Greetings, calculus students and general seekers of truth. Welcome to the video on justifying and showing the formula for the area underneath or inside of a polar curve. So let's say that we have a curve here that is formed by a polar function, r equals theta. So this is, like r of theta equals something. It doesn't matter what it is right now. We want to know what is the area of the region that's bounded by the axes and the curve. Now, before we can get into this, let's review a little bit of geometry, and then I will show you how the geometry relates to our calculus problem. So we know that if you were given a circle, then the area of this circle, let's say this with the length here was the radius, r, so then the area of a circle is pi r squared. Now, what about the area of a sector? So let's say I form a central angle here, and then I want to know what is the slice of this piece, what is the area of this piece of pi slice right here. So we'll call this a sector. Well, traditionally what we do is we set up a proportion that sector over area, or over circle. So area of the sector over the area of a circle is equal to theta over 360 degrees. Okay? And this makes perfect sense because if theta was equal to 180, you would have half a circle, and the area of the half a circle is, well, 1/2 times the area of the circle. Now, in Algebra 2 and beyond, we stop messing around with degrees and we start using radian. So let's convert it to radian. Okay. So instead of 360 degrees, I have 2 pi radian. And instead of writing circle, I'm just going to write the formula for the area of a circle. And then just multiply, do some algebra, and we get this result that the area of the sector is equal to theta times pi r squared divided by 2 pi. So now the pi will cancel. And it leaves us with a formula that says the sector is equal to theta times r squared over 2. Okay, so this is a nice formula for the area of a sector. Okay. Now, you're probably thinking, what does this have to do with the problem, with the calculus problem that we're dealing with here? Well, if you think about this picture here, it's really a circle, except that the circle changes, or the radius of the circle changes. So when you have a parametric curve, so let me just sketch an example here. So let's say you have something like this that looks kind of like an apple. It's basically, you're tracing out a circle, except that the radius changes at different times. So the radius here may be longer than the radius here, and it may be different than the radius at some other point as you go around. Okay. But we can apply this concept of the area of a sector to finding the area underneath a polar curve. So one thing we're going to do is we're trying to find the area here from where theta is equal to 0. So I'll say here theta is equal to 0 radian, up to here where theta is equal to pi over 2 radian. So what we're going to do is we're going to cut up this shape into a bunch of little slices. Okay, so I've taken this picture and I've cut it into a bunch of slices, and I'm going to take the area of this sector here. So this is the one little pi slice, and then this curve right here out here is another pi slice, and then this curve right here is another pi slice. And then this curve right here is another pi slice. Okay, and of course, this is not an exact answer. It is an overestimate, possibly. Okay, but hopefully you can look back at the Riemann sums, and this is sort of like taking a Riemann sum, but instead of using rectangles, we are using sector slices. Okay, and if you can see here that r, each of these lengths here, is the radius. So this is R1, this is R2, R3, R4. So I'm using 1, 2, 3, 4 slices, and we're using the radii that is the smaller of the two, so we're ignoring the last one here. Okay, and so the estimate for the area here, so the area is approximately equal to this formula applied 4 times. And you know, so let's say we divide theta into 4 equal pieces. So we'll just call each of these the angle here delta theta. In other words, the difference between this point here and this point here. So this is delta theta. Whatever it is, you know, it could be, if it's 90 degrees and it's divided into 4 pieces, well then that would be 22.5 degrees. But this measure here is the change in theta, or the change in the angle. So we call it delta theta. So the area here is really equal to R1 squared times delta theta over 2 plus R2 squared delta theta over 2 plus R3 squared times theta over 2 plus R4 squared times theta over 2. Okay, times delta theta rather. Delta theta over 2. So we can expand, or we can condense this and say, just pull out the 1/2, and we can say here that this is R sub I squared times delta theta. I in this case is between 1 and 4. Okay. And hopefully you can see that this is really similar to a Riemann sum. This is called a justification, not a proof, so I'm going to omit some of the major technical details, but I'm trying to give you an intuitive understanding of this rather than a rigorous proof, because that's just in the interest of time. So I'm going to take it down here and finish the problem. So the area is equal to 1/2 summation I equals 1 to 4 R sub I squared times delta theta. And again, this is only an estimate, not an exact answer. But we know that in calculus, our common mantra is, you want more accuracy? Well, the answer is simple. Make more intervals. Okay? Make more intervals. So in other words, if we want to get a better estimate, just cut it up into smaller slices, smaller sectors. And if we cut them up small enough until they are infinitesimally small, then we'll have an exact answer. Okay. So you want an exact answer, make infinitely many intervals. And you've seen also before, when we deal with adding up an infinite number of anything, eventually it comes down to taking the integral. And again, this is a justification, not a proof. For the proof, I would expand on this delta theta and do a little bit more work and take some limits. But I'm trying to give you a big picture understanding of the ideas here. And then we're going to add up an infinite number of radii squared times d theta. So as delta theta gets smaller and smaller and smaller, we represent it with d theta. And we're going to integrate between theta 1 and theta 2, where these are constants. So in the example of our problem here, we would integrate between 0 and pi over 2. Okay. And so this is a wonderful little formula that we could use, if we use it wisely, to compute the various areas of a polar graph. And hopefully this gives you some justification and understanding of where this formula comes from. And with this in mind, we can proceed and take a look at one more example where this formula gets put to good use.